Good evening, folks. In lieu of Randy, I'm going to introduce our guest speaker tonight. Welcome Jeff Stuparits from up in the Gainesville area to our GARS meeting. Jeff is a BSEE, a graduate of Michigan, University of Michigan, MBA from Old Dominion, and retired from Verizon. Spends his time now at a full QRO capable station, but on his his QRZ page says he often works 100 watts in a wire or QRP. But he chases down that demon noise that we all dread to hear on our receivers, especially on the weak signal work. So Jeff, tell us how you do it. I understand you've got a better method than a hammer beating on the telephone pole.
Yeah, I tried that. It doesn't work, but I wouldn't recommend it. Well, I've spent a little bit of time learning a lot about finding noise, so I'm going to try and pass on some of my experiences, good and bad, this evening. And I'm going to be moving around the stage here a little bit. Let me move this guy over. So, things we'll be talking about tonight about what PLM is and why did I need a different approach for my problems. Talk about a thing called an RFI mapper and how it works. And also talk about HTs and Yagis and using those to find noise. So the presentation tonight is kind of two pieces. The first part is about RFI mapping. And the second part is a little simpler approach using the Yagi, a 3-element Yagi, and 137 megahertz and attenuator to find the noise. So two different pieces to it. The Yagi is a little simpler way to start, and that's what I recommend for most people. We'll talk about that as we get into it. So on with the presentation. So what is power line noise? Well, it's radio frequency energy, and it's generated by arcing. If you think back to 100 years ago, that's how they transmitted things. They had a spark gap transmitter, and it was very broad, dozens of megahertz wide in some cases. In this case, it's caused by two pieces of metal on a power pole. And the effectiveness of this arc is the same as it was 100 years ago. It's the size of the arc and how well the antenna is coupled to the source of that arc. And it can range from, you can't hardly hear it, to well over S9, like 34 dB over S9. Lots of different causes. Two most common: defective insulators, defective lightning arresters, and metal-to-metal arcing on the pole. If you have any questions during the presentation, just stop me. I'd be more than happy to answer any shorter ones. If they're longer, we'll just take them on after the meeting. So how do you know if you have PLM? Well, you power up your radio, you pick your band that you like to operate on, you find an unused frequency. It helps if you go to AM mode with the normal AM filter, 6 kilohertz. And if you hear a raw buzz, that's probably, at least it's some kind of radio frequency interference. It may come from power lines, it may come from other things too. So you have to be concerned about what's coming from inside your house as well as what may be coming outside your house. And you always need to investigate it farther. If you hear that, you just can't blame it on the power company right off the bat. So here's a little clip I'm going to play of a pole about a block away from me. I captured on my very old TS690 transceiver. And you can see what the S meter looks like. It's well over S9. You can hear a little variation in the noise too, which is frequently an indicator that it's power line noise. So how do you find this kind of noise or any kind of RFI? Well, lots of choices. One is use a rotatable antenna, HF antenna. To get a direction. Of course, you don't know how far away it is. It could be a block or it could be a mile. You can use your AM car radio, drive around. That works somewhat well. You can kind of calibrate your radio to to know exactly how strong it is and whether it should be a potential interfere. You can use a handy talkie, usually set to 137 or 440 megahertz, and use a Yagi, walk around. That's kind of a slow way of doing it. I've done it that way before. You can also use an ultrasonic dish. We'll have a picture of that a little later. That's what the power companies use. If you can narrow it down to a pole, they'll usually pull out their dish and scan the pole. So all these are good tools, but only one is HF, so it may or may not be the best tool to find your noise. It's a one-by-one search and document operation. I mean, it's kind of slow, especially if you're walking the territory, having to move around, and it may cover blocks or miles. Difficult to quantify the magnitude and the impact of each source, and a very slow process for many noise sources. So if you're tracking one, they work pretty well. If you're tracking 3, 4, 5, or maybe a dozen intermittents, very slow process. So why did I need a new approach? Well, I had about 10 years of power line noise. Sometimes it was big, some small, some constant, some intermittent, and the intermittents are really difficult to find sometimes. Some active when it's wet or cold or hot or dry, and it's just all over the board. It doesn't always go away when it rains sometimes, so they can be just as bad when it rains versus when it's dry. I had an HF beam. It gave me a general direction, but it doesn't really tell you how far away the noise source is. You can usually get it down to 5 or 10 degrees in azimuth with a HF beam, a good one. Very tedious, time-consuming, walking the roads, trying to find the noise sources, and you do some comparison, like, is this the thing I hear, or is it not the thing I hear? VHF noise, which is what I typically use close in, VHF Yagi, doesn't always correspond to the HF noise, so you have to keep that in mind. And sometimes the noise is actually an HF-only noise. Like I ran across a PC power supply that was generating HF-only noise around 4 megahertz. So that you have to track a little differently. But I found generally most times you can track things at the VHF level, and that gives you the ability to use like a 3-element small Yagi you can carry around. So after a lot of years of work, I could never get the noise under control. I mean, I really tried. I worked with the power company. We found things, we fixed things, but we could never really find all the noise that was bothering my location, and sometimes it was quite strong. And the final straw for me was I had a very persistent S9 or above noise to the southeast, and the power company guy and I spent days trying to find it. We walked around, and we found noise sources, but they never seemed to be of the magnitude that I thought they would be because of the strength of my home station. So finally I said, I'm getting really frustrated with this. I just can't seem to control this. It seems like every week something new's popping up. So around 2015, Christmas break, I bought a GPS and wrote some code, very crude at first and refined over the years. And my solution was, how about a color-coded map that shows the location and the strength in the S-meter readings of the noise on the HF band you choose. So if you only have really bad noise at, say, 20 meters, you can kind of track it there. I usually tend to track up at 10 meters because it provides a little better resolution as far as which pole is causing the problem. I can usually narrow down the noise with the RFI mapper down to plus or minus a pole. As I drive around, I use my laptop and it announces the S-meter level every 10 samples, so I can kind of get an idea, yeah, this seems to be a bad area, I need to explore it a little more. I've used the map many times. I sent it to my power company rep, and it's usually pretty obvious where the pole is, and I usually indicate it to the guy I worked with, Vic. I think that this is the pole. And he'll go out and he'll usually test that pole with his ultrasonic dish, or one pole either side. That usually narrows down the part on the pole, whether it's an insulator or lightning arrestor. So we'll look at some examples here in a second. Here's the scale I use when I do the mapping, and you can kind of see let's see, where did I put my stick? Did I drop it already?
Is it not on top of the...
Oh, here it is. There it is. So green colors, cool colors are okay. Yellow is starting to get a little noise, orange, red, and I ran out of colors, so I went to a white, a black, and then a black star. And when they get up into this range, things are pretty bad. If there's a noise source even out to a mile and it's up in this range, I can usually hear it quite easily. So anything above about an S11 is a red flag to me. I can hear things that strong quite far away, and we'll look at some examples. I had to modify the S-meter scale a little bit because I wanted to keep it simple for mapping and to talk to my power line person. So when I get over S9, I use S10, S11, S12, even though they really don't exist. And each one of these is incremented by 6 dB. So S12 would be S9 plus 18 dB in the real world. So you'll see that on some of the maps. So here's the first case I worked on, and this is actually the one that more than motivated me. I was, like I said, frustrated to make this RFI mapper system. My QTH is up here, and it's 1.7 miles, so it's way up here. I had this really strong noise to the southeast. It was above S9 most days. And when I started recording data, I drove down this road and a couple of side roads, drove over here, drove down this way, and the whole time the system's collecting data points, one data point every second. I got down in this area, and you can see what happened. It started going wild. You see some stars down here, and there's some dark colored dots beyond the red dots, and this was the problem. And I also drove this route back here, but it turns out this area back here was very noisy, but it's behind this hill. So I really don't hear that noise, even though it's there. So I wasn't too concerned about that. But got over this area and I said, yeah, that's where my noise is coming from. It's not this up here, which we looked at for days. It's not this. And there was some other noise back up here just a little bit. Those weren't the big problem. It was down here.
It's a significant distance from your house, isn't it?
It is. And actually, I can recall back in 2015, what I started to do, I said, my noise is to the southeast. I'm going to drive every road till I go into Lake Lanier. That was my viewpoint is, I'm just going to be a kind of a dumb guy and not assume that I know where it is. And I just said, well, this is as far as I can go, and this is a lot of water out here, right? So I just drove every road, but when I got over here, I go, okay, I can see why I never found it before.
Where are you on Lake Lanier? What's the left? Is that the Chesapeake?
I think this is 4 Mile Creek here, and 2 miles way over here, and 6 miles down that way some. So this is 369 Browns Bridge Road, and I think Jotham Down is right over here. You know where those roads are. I'm not actually on the lake, I'm maybe a mile or so away. So what was the problem for that one? It was this bolt. And this bolt was arcing to another bracket. The lineman went up to the top of the pole with his bucket truck. He said he could smell something burning. It was the creosote or whatever they use on the poles was actually hot because this thing was arcing and this bolt was about halfway eroded. So they re-drilled it, put a new bolt in it, and my noise went down from this S9 plus 10, dropped to S3. So most things are insulators, lightning arresters, stuff like that, but every so often you get a really, really odd one. You just never know. And they did a great job in fixing it once I found the pole.
Jackson EMC?
Sony EMC. So here's a second example. Actually, it's not my QTH, it was somebody else's, but I drove in on this road, took this route, came back this way, and then back out of the subdivision area and back up again. I went home and I mapped the data. You can see 3 trouble points here, and you have the ability in the mapping program, which is at Google My Maps, you can highlight levels. So these are the hot levels on this drive. You can see this one's especially hot. It's got a blue star. So I focused on that area as far as the problem for this particular person. Here's a close-up view of the actual route. So I drove in. You can see it peaked right about here. I drove down. When I drove out of the area, it peaked right about there. And sure enough, on Google My Maps, there's a pole sitting right here. That was the pole. And it was peaking at S9 plus 18 dB, which is a pretty hot hot pole, and it was the pole top insulator was bad. When you send this kind of stuff to your power company, initially they kind of blow you off like, what this guy talking about. So it takes a little time to build up credibility with your power company rep, but once you do, it starts to go really smoothly, and now my power person and I get along really well, and I send him something, he's out there usually within a couple days looking at it and trying to pinpoint the hardware fault. So here's a third example. You can see things are looking better on my drive runs. This is after a couple years of work. Had some noise pop up over in this area after a kind of a nasty storm went through. And I had a peak reading right here in front of the middle school. And you can see how bad this was, how much it noised up. This is about a quarter mile away, about a quarter mile down this road. It really noised up a huge area. When I was working on this one, standing out in front of the middle school with my Yagi swinging it around, the officer came out of the middle school and said, "We have a report of somebody out here doing some odd stuff." His parents were driving in. I kind of said, "Yes, sir, I'm out here looking for noise." And he was real nice. I explained what I was doing. He says, "Yeah, well, we do the same kind of thing when we go to locate people with ankle bracelets." I said, "That's exactly right, same thing." He also asked me, he says, "Well, my handy-talkie worked better." He says, "It doesn't always work very well in this area." I says, "Yeah, when we finally fix this problem in a couple days to come out and fix it, it should work better when you're out here directing traffic. Because it can be an interfere up at their frequencies, 150 megahertz, or up around the commercial bands, 400 megahertz. So these things can be really nasty, especially if you're near these guys, right? If you're operating, like this guy could stand out in front of the school, probably only 50 feet away from the pole that had the bad arrestor. And it's not going to make his handy-talkie work very well. He's going to have a real hard time getting incoming reports. So fourth example we'll look at, and the last one, is this area was really good until a storm in 2018. I knew the noise was to the south east again. I drove the route, and there were some peaks here and there, but the main peak was right here. And it originated on a pole right at this corner, and we actually fixed a problem up here also, but this was the really nasty one. And it was a real difficult pole because in addition to the pole top insulators, they had something called a recloser, which is like a circuit breaker, and that had all kinds of problems. So it took us about 3 visits to actually clean this up to the point where it wasn't making significant noise anymore. But they kept with it, and the Shawnee Power did a great job locating the problem and spending time. And those reclosers are very hard to change out because they have 14 kV on each leg of the recloser, so it's kind of a tough area to work. So how does the RFI mapper operate? It's pretty similar to what cell phone companies have used. I work for a cell phone company, so I was familiar with the mapping. I looked at enough of them over the years. And the process it uses, every second the GPS dumps the lat long to your laptop. And then this triggers the software to go read the S-meter. So it asks the radio, in my case an old Kenwood radio. We also use a K3, a friend of mine uses a K3. It asks the radio for the S-meter reading, and since you're listening to an unused frequency, like a quiet frequency in the band, you're just reading ambient background noise. You don't want a conversation going on there. And when the radio responds, it records the S-meter reading to the hard drive, saves it in a flat file. So you get 1 sample every second, which works out pretty good up to about 50 miles an hour. And 60 samples per minute, 30 minutes. That gives me about 1,800 data points in 30 minutes, half an hour. And in 30 minutes, if I drive about 20 miles an hour, I can do about 10 road miles of data. So you can see in half an hour, you can collect a lot of data. And you'll probably find 6 or 12 or 20 actual noise sources, some of which are not going to be problems. But you want to look at the full picture to decide what needs to be worked on. As far as what it takes to do it, once you get the flat file, you can map it with something called Google My Maps. I looked around a lot on the internet, finally ran across My Maps, and it's really simple to use once you've used it one time. You basically import the flat file, and then once you import it, you can color by the intensity of the S meter, so you can turn the S meter readings into red, green, yellow, whatever. Hardest part of doing the RFI mapper, and I'm not real good with development tools. It's been a long time since I've done development, but a little bit of patience and persistence will usually get you through the Microsoft stuff, especially if you're good with laptops to begin with. But that's the hardest part, is loading Microsoft Visual Studio, checking all the right boxes to get it to operate properly, and then away you go. So what does the RFI mapper look like? And it's really simple, about as simple as you can get. You need an HF transceiver with an antenna. A lot of guys have mobile setups already. You need a laptop computer, and you need a GPS. GPS looks something like that. That's the box it came in. This radio I have is so old, I needed something else. I needed a TTL converter to get it to RS-232. TTL is like 40 years old, right? Really old. But that's what I had to work with. And then I get it to RS-232, and then I bring it up to USB so the computer can talk to it. So very simple. There's 3 major components, and that's about it. And the rest is the Google My Maps and producing the image that you can share with your power company person. So what does it cost for building an RFI mapper? Pretty inexpensive. I had a laptop computer. Most people have an older Win 7 or 10 computer. I had an old HF radio, Kenwood 690, which works really well. A friend of mine uses a K3. Need a mobile antenna. I usually use 10 meters because it provides a good definition and the antenna is not too big. You want to keep high in frequency if you can find the noise at that frequency. Sometimes you can't. Sometimes you need to work down to 40 meters or 80 meters. But most of the time, noise will be broadband and extend all the way from the AM radio band up into VHF, or some people even use UHF 440 megahertz. It gets a little short range there. You have to be kind of close to the noise. So I like working down at 10 meters most of the time. You need Microsoft Visual Studio, that's free. You need the RFI Mapper program, that's pretty straightforward. So it only cost me $29 and some development time to put the pieces together. And like I said, for my radio, it's ancient, probably more than 20 years old. I had to have the converter, which I happen to have one around, to get it to RS-232. And then I needed to get that up to USB. Word of warning, if you use any USB to RS-232 converters for whatever purpose, whether this or something else, don't buy the ones on the low-cost internet sites. My first encounter, I borrowed one from a guy at work, and when that worked, I actually went out and bought one. And I picked up one of the ones off one of the discount sites, and I got in the car, and the truck rather, and started to drive, and I go, man, the noise level's S9, and I'm in my own yard. And it turns out the internals of that converter, they use like a little circuit that does neg 12 and plus 12, and gets that from the 5 volts. And if they didn't properly design it, those things are noisy. I mean, you won't hear anything because the converter, little dongle kind of converter, makes so much noise. So after looking around a little bit, I settled on this Brent converter, and it's really good. It makes hardly any noise at all. So be aware of that. You may, if you go on discount sites, you're going to potentially find something that is extremely noisy. It may not actually be legal because of the amount of noise it generates, and you don't want to have that. You want to be down around S5 or so in the mobile to be able to detect power line noise and other kinds of noise.
Got a question out here.
I was curious if you've considered using those little SDR dongles for this?
Yeah,
RTL type?
Yeah, I played with one of those, and you definitely can use one. The reason I don't is I already have enough challenges running the laptop,
Okay.
and then the SDR dongle runs through the laptop, so you're constantly flipping windows back and forth between the two. Maybe if I got really, proficient at doing that, I'd be okay. But right now, I just want the radio to do its thing. Kind of a dumb approach, basically. And
Keep it simple.
Yeah.
Keep it simple, right?
Yeah.
Okay.
I tried playing with that, but after basically 3 or 4 hours, I just said, this is more complicated than I want to do while I'm driving, because your attention's on the road. You don't have time to mess with the laptop, and I can just basically just touch the volume control, turn it up and down the radio. If somebody happens to come on the frequency I'm on, I can just spin the dial and I'm away from that person talking.
What antenna are you using when you're driving?
I have a 10-meter ham stick. It's probably 20 years old, so it's about 8 feet long or so. It's on the back of my pickup truck. It's a good compromise between trying to stay in the higher frequency range versus the size. You can go down to lower frequency if you're trying to noise down, say, in 80 meters, but if you go too low in frequency, a wavelength at 80 meters is quite big, so you may not narrow it down to a pole. It may be 2 or 3 poles. I would just as soon hunt it up at 28 megahertz where the wavelength is relatively short, and as you move away from that pole, it tapers off really quick. So you get a pretty clear definition. So all the maps you saw earlier were all at 28 megahertz. You can kind of see where it scales up, and it scales down really quick as you go closer to that pole, then move away. If you're on 80 meters, you won't see that as distinctly. You're going to see a slower taper as you move away from the pole. But it will work. So what does it look like when it's running? Here's a little snapshot I took. I call it a simulator mode. You have the ability in software just to say I want to be in simulator mode where it just fakes out the latitude, longitude, and the S-meter reading, rates random numbers. It allows me to work with the software and make changes to it. So it starts off, it announces itself, it tests the GPS to make sure it can talk to that, it tests the radio to make sure it can talk to that. You have a chance to input the file name you want to use, and it goes into a mode of collecting data. You can see it collects the latitude, longitude, the elevation actually, not altitude, number of satellites it can see, and then the S-meter reading, which is coming in every 1 second. And like I said, a simple flat file up to 2,000 data points, and used to import it into the mapper program. So once you get this flat file, it has the data points. What do you do with it? Really pretty simple. You import the CSV file, which is a comma delimited file, and you style, that's what the term they use, the map by the S-meter level. I change the icons to circles, which are a lot easier to interpret. And it colors the circles by the S-meter level. And you also have a choice to pick. You can go either satellite view, so you see buildings and poles, like that one picture we saw, or you can also look at terrain. And the terrain is rather useful sometimes because sometimes the poles can be on hills at quite a long distance away. And I ran across some of those, and we'll talk about that in just a second, a couple of interesting cases. So once I get the map, identify the close issues to my QTH. In other words, if there's one that's pretty strong a half mile away, you probably want to work that first. I pay a special attention to anything over S9, even though it's a little farther away. When you start getting above S9 on the mapper program, it can be a problem a mile or farther. If something's on a hill, and that's one of the reasons you want to look at the elevation, either from the data you collected or from the mapping program, which shows hills and things. If it's on a hill, you might hear it for quite a long time. And when I collect the data, I usually rank the top 3 or 4, and I go out and do a little more investigating before my power guy comes out and sweeps the poles with his ultrasonic detector. The idea is you want to spend the time on the poles that are really causing you problems, not the ones that are just S3 or S4. You want to work on the big ones.
What software app was that? Visual Basic that you wrote that?
Yes.
Okay.
Yep. Actually started out like most of my projects as a little test, right? So I used some code over from some other work I'd done, and that was written in Visual Basic. I just added on. Before you know it, you have everything written in Visual Basic, and it's plenty fast enough for anything we do here, so I just stuck with it. And it's real simple to modify, too. So clearing distance guidelines. After messing with this for 4 years, I've developed a guideline I use. If I have wire antennas, or if somebody has wire antennas, generally you need to clear out to about 1/4 mile. That's just a rough rule of thumb. It kind of depends on how strong the RFI is. But if you have a 3-element beam, you're going to probably have to go farther, at least out to 1/2 mile. If you have something like at 100 feet and it's a multi-element Yagi, you may have to look out as far as 1 mile. And if you think about a mile circle around your QTH, that can be quite a large area to cover. And that was the problem I was having is there were just too many noise sources and I couldn't decide which ones were important. When I did know the direction, I'd have to go out and walk for basically miles, and I could never really nail down the right ones. So my setup's a little unusual. I have a 5-element at 90 feet I use a lot. Noise level now runs around S1 or S2, so it's pretty good. If not blocked by terrain, I routinely hear large sources out to 1+ miles. My longest confirmed one was that first example I showed, 1.7 miles down a creek valley. I would have never thought to look that far out until I just said I'm going to drive until I hit the water. And the longest suspect pole was a pole on a 200-foot hill in the distance. That was out 3 miles. Once they cleared it, my noise went away. So I'm pretty confident that was my problem in this case too. But I wasn't actually on the radio when they cleared it. But 3 miles is a long ways. And even my power company person said, I thought I thought you could only hear up to 2 miles. And I said, well, that's true normally. But this is a special case, right? It's on a 200-foot hill or basically a 200-foot tower and it's generating RF. You can hear those things a pretty long ways away. And a lot of this depends what you're doing. If you're a DXer or a contester, that's kind of important because you want to be able to hear the DX or the new multiplier or workstations, and you don't want everybody, or you're not going to have everybody producing an S9 or better signal. A lot of these guys are S3, S4, S5. So what do you do once you say, I think I found the right pole? What do you do with it? You got to open a trouble ticket with your power company. Sometimes you'll get in contact with the power company engineer. Sometimes they just send somebody out to look at the problem. I always like to try and talk to the engineer if I can, so I can be out there when he's going to go out and look. You don't want to give them 20 things to chase down. They're going to blow you off and say, this guy's out of his mind, 20 things. You pick the worst ones, the ones you think really affect you. And if you do a map, you can evaluate in a particular direction, especially, which ones are the likely culprits. And some folks say, well, you should just be working on the most significant noise source, just one. What I found after doing this for a while is, yeah, you can work on the biggest one, and then next month you get to work on the second biggest one in that direction, and then the third month you get to work on the third biggest one in that direction. So now when I look at it, I just say, well, how many things are likely to affect me? And those are the ones we work on. As long as we're getting a line crew, you might as well get out there and say, these are 3 big problems. They're all in the same direction. Even if we clear the biggest one, it's still going to be noisy. I'm still going to hear number 2, number 3. And as long as the line crew is there, it's much more efficient for them just to go a block or 2 down the road and fix that problem while they're there on site. It works real well. They can, a good line crew can do at least 3 poles or maybe 4 poles in a day. When they do go out, always offer to be on site with them. That's really important to help them out because they are experts in the power poles and the hardware on the power poles. But we as hams are experts in the HF part of it. So you'll want an HT, a Yagi, and probably an attenuator. After a few of these, you'll get a pretty good working relationship with the power company. You can help them and save them a lot of time. They don't have to go out and spend hours looking for problems. Matter of fact, I was talking to one of them. I asked him how he normally found problems, and he said he took his ultrasonic dish, put it out the window, and drove down the street and tried to scan the poles. And I said, that's not very efficient. Driving down the street's not real safe either, but it's not very efficient. And he goes, yeah, it's much better if you can get me to the right pole.
Correct me if I'm wrong, but aren't they also, this is advantageous for them to find this because this is lost energy, lost power that they would love to be able to reclaim by not having it go to ground, correct?
Yeah, that's what I thought too, and I think that's a correct assumption because you are drawing a lot of current during that arc and it's putting load on the poles. But it seems like, for the most part to them, they're not as concerned about that as making sure their customers, you, are happy. Okay. So even though they do lose some power, and we realize that as hams because we deal with power, they're more concerned that you're happy, number one, and number two, there's not going to be a safety hazard. Like that first example we looked at, that bolt would have eventually broken off and the cross arm would have either flown up or down or fell off or whatever the case So they're very interested in safety issues especially, and I think that one kind of keyed them in that, yeah, we should pay attention to these hams because this could be a safety issue, if nothing else.
Have you shared your program and your method with them, and have they shown any interest in adopting it themselves?
I've only had one power group show interest. They more or less rely on us to report the problem. They're not too interested in going out and be proactive unless it's causing either a safety issue or a problem for us as radio receiver people, some kind of reception person. Now, this also affects other services besides us. I'll give you an example. I was working on one problem with my power guy, and his friend came to get the ultrasonic dish, and I asked where he was going, and he said, I'm going up the road here, AT&T reported the problem. And I said, well, we're finishing up here, would you like some company? He says, yeah, sure, come along. So we drove up the road 2-3 miles away, we stopped, and I kind of did a little survey with my truck. I drove through the area back again, and I pulled off. We got out of our vehicles, and we started walking down the road. I took my Yagi, I swung it just once around, and I said, nope, you're going in the wrong direction. It's that pole right there. So he came back and he walked over and he scanned it and says, you're right, that lightning arrestor's bad. So as RF people, there's a huge amount of benefit we can provide to the power company. Get them to the right pole. That's our purpose, is we're the RF experts. And getting it to the right pole is going to help them a whole lot. So in that case, it was a lightning arrestor. It was interfering with the DSL hardware on the pole and putting some customers out of service. So they were thankful that I spent a few minutes working with them. So you're going to want to send the power company an email if you can, maybe not the first time, but after you build up some rapport. Give them the 3 or 4 things. They're going to use something called an ultrasonic detector. A radar engineer makes one. It's about $2,000, so it's a very pricey piece of equipment. And they can usually narrow the issue on the pole down to a particular piece of hardware. Not all the time, but usually you always want to offer to be on site when they come out. Sometimes they'll say yes, sometimes they say no. So does the RFI mapper work? Yep, sure works very well. Been using it for 4 years. Probably identified over 1,000 sources. Fixed, I'm sure, at least 100 of them. Saves the power company a lot of time because we can get them usually down to the pole, plus or minus the pole. Once you actually clear the problem, you can redrive the route and show that the area is all green again. After 10 years of me trying to fix the problem doing the Yagi only solution, I really got my noise under control. Now I went from S9 or more. I'm now down to like an S1 on 10 meters, and that's an AM mode, so when I flip over to sideband, that's about an S1/2. So that's my northeast and northwest directions. My southeast, southwest are still a little noisier. My biggest concerns now are intermittence. That's the audio clip I gave a little earlier. There's something to the east, block or 2 away, shows up for about 4 or 5 hours, and before I can get out there, it's gone. So I need to catch it when it's bad and when the light is daylight. I don't want to do this stuff at nighttime.
Is that the guy with the welder?
No, there's actually a welder up at the school. They're building a school near me, and I can hear that guy. It's a real broadband noise, and you know when it's on because you point towards the school. And when it idles, it's not real bad, but as soon as they start the arc, it just, it wipes you right out. So here's a picture of kind of when I started in January of 2016. I'm down here, and major problems. Here's 1, 2, 3, 4, 5, 6. 6 problems identified that needed, and there are other ones there, but those are some really big ones identified as needed some work. You can see why I had a problem locating some of these things. So this is a couple years later, August 2018, redrove the route. Most of it's pretty green, and a little problem here I was working on. This is the one in front of the school, bad lightning arrestor. And this is also a bad lightning arrestor. They fixed these 2 problems, and the rest of this route turned green. So I've made a lot of progress, more progress to come. This is a little view of what my noise level looked like back in 2016 again. You can see September, And then it got colder in October. Here was my noise level in September. Not too bad, S3, worst case. And then it got colder weather, and it popped up to well above S9. What I've kind of found is there's two sets of noises. I call them warm weather noises and cold weather noises. And the two are different. So you may clear all your problems during the summer. And the minute that first cold spell hits, there's a different set of problems. And the warm weather problems may go away, and the cold weather problems may pop up.
Have you identified a temperature changeover?
Right around the freezing mark, or like the 40-degree mark. So about 40 degrees and less and dry, different kind of problems.
You mentioned mostly power line noises here. Are you looking at any other interferences rather than power line noises?
Yeah, we'll talk about that in just a couple minutes. So here's a snapshot of a couple years later, August 2018, and here's what my drive test provided as far as noise. Looks like this was August. You can see it's pretty good. And let's see, Europe, it's less than S1, and this is again in AM mode, 6 kilohertz. So it was greatly improved. I can hear things now. So that's half of the problem. That's what I call wide area network, WAN stuff, to borrow a term from the computer industry. But you don't need to start there. You can start doing the local stuff, and the tool I use for that, HT, that does aircraft band, AM mode, and 137 megahertz Yagi, works really great when you're trying to help the power company people, because you can take this thing.
Why 137 as a specific frequency? It's wide band. Wouldn't any frequency pretty much work?
2 meters would work, but the reason I like that frequency is when you're working with, let me just grab it here. So I have the Yagi here, which is nothing more than a broomstick handle and 10 gauge wire for the elements. So it's really a zero cost. I attach it to a piece of coax. And the nice thing about the Yagi is if you walk around and bend the elements, you simply bend them back. That's a real good thing. I have an attenuator that provides up to 45 dB of attenuation. That's 4 slide switches and 12 resistors. That's all it takes to make one of those. And an HT, a Yaesu HT. The reason I like 137 megahertz, 2 reasons. It's a quiet band up at the very top. It's an aircraft band right at the edge. And in the aircraft band, your HT does not transmit. If you're in the 2 meter band and you hit the PTT button by accident, the tiny resistors in this box are going to go smoke, and you're going to see smoke come out of the box. Then you have to redo the box again. So I've never done it, but I've come pretty close, so I kind of wised up and said, I'm going to do all my noise hunting down at 137, because I can't possibly burn up my attenuator setup, and it's not a real good idea. It's kind of embarrassing if you're out with the power line guys and you actually hit the PTT and you burn up your equipment and say, sorry, I can't help you today. So I've stayed away from that problem. One thing I did learn is these, the PL259s, which I happen to use here, are not the best connectors to use. You see I have this one taped up, and that's because when you're out in the field, this coax will rotate over and over and over again. Eventually the braid gets wrapped around the center conductor of the coax. It exits the coax inside the connector. And I went out one day by myself looking for noise, and I was walking around, but gee, it's really quiet today. Every place I look, the poles are quiet, which some poles are never quiet, right? And I went back in the house, and once I got back home, I swept through the kitchen, and I know there's a coffee pot that makes noise, and the coffee pot was quiet. I go, uh-oh, something's wrong here, because that's my test fixture, right, the coffee pot. And sure enough, the braid on the RG58 had wrapped itself around the center conductor and shorted it out. So my 2-hour exploration into the joining neighborhoods in the fields was useless, right? I was basically looking into a short all the time.
So a calibration before starting is good.
Exactly. Before you go out, check it against a known source. Just basically be a dummy like I should have been, and I tend to do that now to make sure it works. So what do you do with this thing? Well, Well, this is really a must-have when you're working in the field with a power company, because you have to be able to say, it's that pole and not the other pole. When you listen to the noise, the reason I have an attenuator is don't go by the loudness of the noise. If it sounds loud, it may or may not be loud. You really can't tell by the loudness of the noise. You have to go by the RF level. So I've developed a little scale that I use, and I do this by how much attenuation does it take to get rid of the noise. If it only takes 1 to 12 dB, I call that a small emitter. If it's 13 to 24, I place it in the medium. If it's a 25 to 40, I call that a big emitter. If it's more than 40 dB of attenuation to get rid of the noise, that is really a big problem. A lot of times bad lightning arresters will be in this latter area. And in fact, I've never seen one that's been anything less than about a 40, and I've actually seen them as high as a 50 dB of attenuation to get rid of the noise. And that's a big noise.
So if you can actually, if you were talking to somebody and you know how many dB you're at, and you know the radio's probably half a microvolt sensitivity, you can tell them about how many microvolts their signal is.
Yeah.
And quantify it to prove that it's above an FCC limit.
Yeah, but if you're talking to somebody on the radio or talking to somebody next to you.
Talking to the power company.
Yes, yes. Yeah, they appreciate the fact I can kind of gauge the size and tell them, but you don't want to be talking to somebody else for the reason you mentioned earlier. You're transmitting through your attenuator, and it's going to go dark real quick. So this is the scale I use. We'll look at some noise sources internal to my house in just a minute. So one thing to be careful when you're using the Yagi, when you see poles with lots of wires on them, they may not always be the source of the noise. In other words, if you have an antenna with a lot of elements on it, or a lot of driven elements on it, it can generate a lot of signal. Consider that an adjacent pole may actually be causing the noise, but the noise may be running over to the pole with a lot of feeds on it. So I've been fooled by this more than times than I can count, probably a dozen times. When you're evaluating two poles, stand midway between the two poles and do an A-B comparison. So you take the Yagi, point it one way, back the other way. So A-B, A-B, do it about 3 times, and make sure you really have the right pole. And I'll give you an example. I was out with my power line guy, and we traced some noise to a street, and we got out of our vehicles, and I turned the HT on, and I scanned, and I go, hey, it's that pole right there. And he walked over to it, and he started smiling, and I knew I was in trouble when he started to smile, and he walked down this driveway, and said, no, it's that pole in the driveway, and I go, I should have spent a little more time and got on both sides of the pole and done the A-B comparison, because I'm kind of hedging the bet in favor of the pole I'm closest to with the most wires on it, right, the most antenna wire. And you really need to give it a fair comparison and be midway between poles so you can do a more fair comparison between the two poles. So just keep that in mind. I'm sure if you use the Yagi, you're going to learn that lesson like I did. And I try to always just hold my statement for a few seconds until I actually get midway between joining poles and do the A-B comparison.
As far as Yagi orientation, do you concern yourself with the polarization?
Yes, absolutely. Sometimes it'll be vertically polarized, sometimes horizontally. And I think that's partly due to there are ground wires on these poles that go down to the ground rod next to the pole. And if the arc happens to be traveling, or the energy from the arc happens to be traveling down that ground wire, you're going to have vertical polarization. If the arc happens to be traveling on a neutral wire going to the next pole, it's going to be horizontal. But I'm constantly flipping back and forth, and there will be obvious peaks in a lot of poles. Yep. So what causes noise inside of our QTHs? And here's a list of my offenders. I have a router, like most people do, with a cable modem, a router, and a VoIP unit. And it produces a plus 21, which is a pretty decent size interferer. At least when I started, I've tuned it down a little bit, and on 80 meters it was an S7. So if you have a router, cable modem, the VoIP unit wasn't too bad. It was mostly the router and the cable modem. The other offender was a Mr. Coffee LCD coffee pot that was produced in the plus 18, so still in the kind of the moderate size. I now unplug that or don't use it when I'm contesting. And I also had a Dynex TV from 15 years ago. That was about a plus 12. So I walked around my house with a notepad doing sweeps, and I'd go, boy, that thing's making a lot of noise. So you want to record what it is and how much noise it's making, and when you're all done, you can kind of rate the things you want to look at. But I'll just about guarantee you can walk through almost any house nowadays and find stuff like this. And what it was mostly, in this case, really two things. This router had a switching power supply on it, and switching power supplies can be really noisy on the low bands, like 80 and 40 and 160. So you want to convert or change those out to linear power supplies. So it's a little lightweight thing that weighs about 3 ounces. Those are usually the switchers. And then the big heavy transformers from maybe 15 years ago, those are the linear power supplies. Those are usually pretty quiet most of the time. So whenever I can, a lot of them are 12 volts, I change them out to the linear types. The other thing we're going to talk about in a second, the cable modem and the router. The cable modem has an RG6 coming into it. I use Comcast. The router doesn't have a ground on it typically. It's a floating chassis. That's a problem. So you can see my S meter reading was S7. That's not overly good when you're trying to hear distant stations. So I mentioned the wall wart switching supplies, really noisy. And on the routers, the cable modem is getting grounded via the RG6. They have to ground that as it enters your premise. But the router has no ground typically. I did a lot of measuring to the antenna connectors, to the negative on the incoming power from the little wall wart power supply, on the cables. It's just floating. So what I did was I took a shielded Cat 6 cable, and I ran it from the cable modem to the router, and it dropped the noise produced by the router by 2 S units. So from an S7 to an S5, I used a little 3-foot piece of cable. The first time I did that, I happened to go to some of the low-cost internet sites. I found some shielded 3-foot RG6, or Cat 6 rather, or you can buy Cat 5e or whatever. Cable, and I bought 3 or 4 of those. I got them, and I said, Joey, they're not as effective as I thought. I started measuring the resistance between the metal shell, that's what surrounds the RJ45 at each end, and I was seeing 2 to 10 ohms, sometimes more, between end to end. I'm going, that doesn't make any sense, right? It's just it's a metal shell at each end. So I decided I was going to sacrifice one, took it apart, and it turns out the drain wire for the shield on the cable next to the metal shell at each end, the RJ45, is just laid across the metal shell. So as you wiggle the cable, the connection comes and goes, and the resistance goes up and down. I go, oh, that's not good. So I ended up being a little smarter. I went to my favorite place, Mouser.com. I ordered some Amphenol cables, and they had a spec sheet where it showed they were soldered to the shell at both ends. They were less than 1 ohms, and they did a really good job. So the router had no ground, though. I verified that more times than I care to count. So I looked at all the possibilities of how that router can get grounded, and it can't.
Well, yours may not, but others can.
Yeah. Well, almost all of the home routers now are running off the switching mode power supplies, not the old linears. And there's just 2 wires coming out of it's the AC socket that powers the switching mode power supply. That then powers the router. There's no ground there, it's just plus and minus. But the switching mode power supply has no green wire going to it. It's just a plug in the wall 2-pin, so there is no ground there.
But you could have just as easily put a piece of wire to the ground of the router and ran it to neutral.
If I could have found a place to attach it to the router, I would have done that. But there was no good place to attach. There's no ground lug or anything. It's just built for home use and not really for an RF environment. But yeah, you're right. I could have maybe opened it up and found a good place to attach to. So
You did the easy.
I just found a good cable so that the router has its ground, and then the metal shell in the router. There's actually a metal shell that typically surrounds the electronics. That's tied to the PC board. that helps some, but you still need some place to send that energy. Otherwise, it's just going to energize the shell, and it's going to be a little transmit. So anyway, I did that, improved my noise level by 2S units, 12 dB, which was a real big improvement for me.
What about LED lights?
It depends. So I today use my favorite, which is the General Electric 2X Life. I found them at one of the big box stores. They produce no noise as far as I can tell. My son-in-law remodeled his kitchen back about a year or so ago. He used can lights in the ceiling, and about a month or so after he finished, he called me up and says, "Why is it when I turn my lights on, my TV goes out? It goes blank." He was doing over the air. I said, "Well, I don't know. Let me bring my Yagi down and let's see if we can find some RF floating around." So I brought it down there, and the minute he turned it on, it just went wild. I mean, it was like a 40 dB noise source. And I scanned the dimmer, and that wasn't it. And I scanned the lights, and they were just going wild. There was, I don't know, 10 lights, maybe, can lights. I said, "Well, where'd you get the lights?" He goes, "Well, I got them off a discount site." And I said, "Well, where's the country of origin?" He goes, "They were made in China." I said, don't do that. Just get something that's made here in the U.S. that needs to meet the standards, FCC standards. But they were terrible. So it's all over the board. CFLs are a little noisy. Some of the LED screw-in type, the A19 bases, are a little noisy. But I found these GEs that had no noise. I use pretty much all GEs now.
Philips. The Philips were the least noisy that I tested.
Yeah, it's a good idea to buy like just one or two, and then I put them in a test fixture, and I have a little antenna that runs by them that goes to my HF radio. You know, I can do an AV comparison between the different types, but the first type I found, they discontinued, so I had to find another type, and that's when I settled on the GE brand. But yeah, you definitely want to investigate that before you end up installing 20 or 30 of those in your house and find out that, no, they produce a lot of RF energy that you really don't want. So what does a power pole look like? We talked about power line noise. You have a high tension wire, usually about 14 kV. There's a pole top insulator. There's a tap off that pole. It goes to a lightning arrestor, usually black. It goes over to actually an insulator that's tied to a fuse. And then that fuse feeds a drop wire. And here's a bell insulator that feeds that. Sometimes the bells are noisy. Sometimes the pole tops are noisy. And sometimes lightning arrestors can go bad because there's ground at one end of the lightning arrestor and 14 kV at the other end. And sometimes the internals will go bad. Matter of fact, one time they were working on a pole, and the line crew went up there, and when he disconnects usually from the high voltage, but when he went to change out the lightning arrestor, it just disintegrated. It had been hit by a lightning at some point and just turned it into basically kind of a dust pile. And once they changed that, the noise went away. Word of warning, don't mess with power poles, don't touch them, don't do anything to them. That includes taking a sledgehammer to the bottom. Always a bad thing to do because you just never know what condition the pole's in. It might have been hit by lightning. It's just not worth doing it. Your job as a ham is to find the pole that's causing the noise with your RF equipment without ever coming in contact with it. So sometimes you get some really interesting stuff, and I had one last year. I drove this route. It's a good ways away from my QTH, maybe a mile or so, and the whole area was noisy, and the road is over here. And you can see the fence that goes along the road for quite a distance, and it kind of makes a corner here and comes along another road. When I drove that area, the map just kind of lit up, and I go, well, what's going on here? So I spent about an hour scanning this pole over and over again from every which direction with my ultrasonic. Couldn't find anything. I go, what's going on? Well, finally, I scanned down. I go, the dirt's making noise. Because I scanned in the area where the fence was, and I looked a little closer and go, no, that's a fence with metal ties, and these ties were generating the noise. And I looked into it a little more, and we were in a drought at that time. It was the one last fall. And what appears to happen is these poles lose ground because the dirt is now so dry that it's not an effective ground for the 1 or 2 feet that's in the soil. And the energy is induced from these lines above the fence. So once the fence is powered, that energy looks for somewhere to go. And normally we find it, every 10 feet in these poles. When the ground goes dry, it has to travel a great distance and go through junctions in order to find ground and dissipate that energy, because it's looking for a ground, right? So apparently what happens is the oxide on these joints forms kind of like a diode and generates noise. So I could scan along this fence and pinpoint it right down to these joints. And that was the noise producer. So you just never know where the RFI is going to come from. We had rain a few weeks or maybe a month after this. Noise went away, hasn't been back since. So weird things happen, and this was one that kind of baffled me for a long time. And I spent a lot of time looking at that pole because I thought it was this pole along this fence here, and that wasn't the case. It was actually that joint.
What about electric fences?
Haven't had one of those yet. I don't want one either. I actually found a second fence just like this in a different neighborhood doing exactly the same thing during that same time period. So once I spent a lot of wasted time on the first one, I got a little smarter and I realized that other fences caused a problem and didn't spend so much time on it. So as hams, we're the folks that know the RF, right? We know how to use Yagis, attenuators, radios, which is our niche. Power companies are really good with their power poles, the line crews. They do a fantastic job. They always do it safely. So your job is to find the source, like the pole or the item that's causing the noise, and their job will be to pinpoint the part on the pole. Sometimes they're not available, so if I'm out and there's an intermittent, I'll bring my dish out, which looks like this. It's an 18-inch dish, a lot like the radar engineer's unit. It's got a little transducer in front that collects the energy. I put the electronics on the back of mine, and I added a little hand grip and a scope, which helps me to find the actual component on the pole. You can sweep, back and forth, left, right, up, down on the pole, and you'll eventually, if you get the right angle, you'll find the defective component. But it's not really necessary from our RF standpoint. That's really their job. But sometimes they're tied up, and maybe a week or two before they get out there, I'll take my dish out and do some scanning. Kind of an interesting thing when you're trying to find arcing, it's all line of sight. And when I say line of sight, you need to be line of sight to it. If it's not line of sight, you're not going to hear it. So I usually scan from about 6 different directions on the ground, on the pole. And some will produce no noise, and other ones you'll walk and go, man, that thing is so loud, I can't believe it. The other thing I've found after a lot of years is it has to be line of sight, but it also can be a reflective surface. So if you have a bell insulator or something hard on the pole, that can also reflect the energy, the sound, and you'll be able to get a pickup with the dish by pointing at that. You have to be kind of careful because it's a false point sometimes. I did a little experiment, and I'll try and keep it in a little.
And that's an audio dish.
That's an audio dish, that's correct. It runs up 25 to 40 kilohertz audio. I did a little experiment. I have a noise generator that it's in a box. It's a spark plug basically with a transformer that makes it arc 60 times a second. If I shoot to the side of it through the plastic, I hear nothing with this dish. Can't pick it up at all. If I turn it towards me, where the hole is towards me, I hear it just fine. So I thought, let me try bouncing that off my truck body. So I faced it towards my truck body and moved about 30 feet away. Had no problem picking it up. Even though I couldn't see the arc, it was hitting the truck body and reflecting back to me, which is basically what a bell insulator would do, or a lightning arrestor or metal on a pole. And I thought, well, let me see if I can reflect it off a different surface. So I put it next to the side of my house, which is brick. Let me see if I can reflect off a brick. And I could. It was down maybe about 6 or 10 dB, but it was still enough of a reflective surface. So when you use these things, you have to kind of think about what's happening. And in most cases, you're going to have a direct line of sight, but the path may actually be buried in the bell insulator, and you may still hear it just fine. One comment, when you're working on these problems, it's a nice little thing to consider. There's something called free space path loss, which describes the loss as you move closer and farther away from a source. And the takeaway on this is, this D is a squared function. It's in this part of the formula. So if you cut the distance in half, the signal goes up by 6 dB. If you double the distance, it goes down by 6 dB. So when you decide where to put your antennas at your home, you want to use that to your advantage. If you can avoid it, don't place your antennas directly over your house, or you can not do it, don't place them in the attic, because you're very close to a lot of noise sources. I did that for a while. I had an antenna in the attic. You want to put it in the backyard, away from other things that cause noise, so you use the path loss from your noise sources to your advantage, so you keep them away. Sometimes you can't do that. Sometimes you just have to put them in the attic. You've got to put them right above your house. But if you can avoid that, it's always a good thing to do, just to eliminate your problems. So RFI locating, 3-step process. First one, clear your local area noise. That's where you use the Yagi. I have some plans for this Yagi. I made about half dozen copies. You're welcome to have it, or email me. Use the Yagi, the HT attenuator, to clean up your house, and anything you can hear in your yard is you sweep the horizon. Because there's no sense in getting in the vehicle and driving miles when you have the pole in front of your house making noise. You might as well start right there. So clear the local area noise. Second, you want to clear the wide area noise, and that's where the RFI mapper would come into use if you have a Yagi antenna, HF Yagi, where you have to work out to some distance, or maybe in your neighborhood. It's a lot easier to do that, build the mapper, and then you have a tool that allows you to clear as far as you want to clear. And the last thing is you work on the pole. That's where you use the ultrasonic dish. It's really a pole by pole kind of a thing. And you can find the bad hardware, or at least have a pretty good idea what the bad hardware is. So those 3-step process pretty much works every time. I've used them for 4 or 5 years now. So that's it. Any other questions? Sure.
Have you found any problems in subdivisions with buried power?
None yet, but we don't have hardly any subdivisions like that. I can only think of 2 cases I ran across. Both were kind of odd, and I don't know what the source of the noise was, and it wasn't bothering me, but I was driving through a subdivision doing RFI mapping, and I got in front of a house. I mean, it was noisy, and this is back about 3 or 4 years ago. I looked around and go, well, there's no power poles here. And so I'm thinking it was either grow lights or some kind of noisy switching power supply, one of those 2 things. But it was pretty localized. And I ran across that same thing about a year or so ago. I drove through a neighborhood and I got to one particular house, and it was real noisy, but it was still shielded from me via a hill, so I didn't have to worry about it.
Well, I
Just never know.
I would think that possibly if they had any type of faults in the cable, that I think the noise may be radiated where the transformers are, since they're above ground.
Yes, I've heard of other people having that problem where you're exactly right. There was a cable, and the cable was arcing to another cable in where it entered the box, but I've not run across any yet. I hear, like, same with exterior problems, that those will eventually burn themselves out, right, because they're arcing like that bolt on the pole. But I have not had any. Usually, if you have underground, your neighborhood is usually pretty quiet, with the exception of the switching mode power supplies people have in their houses.
I've read somewhere that they're actually running into a number of cases where they're finding grow lights for marijuana operations in residential areas. They're putting commercial lights that are not rated for being in residential areas in these houses, and as a result, they're getting all this RFI noise coming out of the houses when they start scanning.
Yeah, we're pretty fortunate in Georgia. We haven't had that issue yet with grow lights, but I hear in California it's a big problem. And the other problem that's happening a lot in some of the sunnier states is the solar panels. Some of the controllers on the solar panels can be very bad. So I've seen a lot of complaints from people in California and Arizona. California especially, where the power is pretty expensive. A lot of people are doing the solar panels to kind of assist in the cost of power. But we've been pretty lucky here so far. we'll see how it goes the next 5 years. Okay, thanks for your attention.